Okay, so do you have any questions before we get started here? No? Okay. So I figured we'd start with a problem on distributed loads. So this is a pretty common thing that you might see. So we have an angled wall here with a gate. And so we know how far down the gate is, we know how long the gate is, and we have water to the left of it, and we know what angle this the wall is at compared with the surface of the water. So now we want to figure out what is the reaction at this end here. We're assuming there's some locking mechanism here that's stopping the gate from swinging open. So we want to figure out, based off of the distributed load here, what that is. So first thing we know is we know it's going to be a distributed load along this gate. So we know what it's going to be at this point here. At the first point, it's just going to be rho g, the height down from here. But we don't know that height. We know the height, or we know the distance along the wall. So we want to figure out what that height is there, and then do the same thing for this point. So we'll call this point 1, and the other end we'll call point 2. So H1 is just going to be, let's see, so we have a 30-degree angle here with 10-meter length there, so that's just what it's going to be, 10 sine 30. And then H2 is going to be, we had the extra 5 meters here, so it's going to be 15 sine 30. So then we can figure out, based off of that, what the forces at each of these ends are. So let's just draw zoom here. Okay, so let's see. So we're going to say the force at this end is going to be rho gh, with rho for water being 1,000 kilograms per meter cubed. So these are both measured in meters. So let's see. Can you sign in, please? Okay. So we have, let's keep our units here. 1,000 kilograms per meter cubed times, let's see, so this is 10 sine 30. Let's just check what that is. Okay, so 10 sine 30 is just 5. And that would make this, what, 7.5? So then, let's see, so it's 9.81. Gravity is 9.81 meters per second squared times this 5 meters. So we know this is going to give us our force here. Let's see. So it's just going to give us it in newtons. And so we end up with 49,050 newtons. That's the force at the top of the gate here. And then we also want to figure out what the force is at the bottom of the gate. So we'll call that F2. And that's still going to be rho g, but this time H2 is equal to so the 1,000 again times 9.81 H2, which we said is 7.5. So let's check what that is. It's 73,575. So now that we know those two, what we want to do is we want to come up with our value for the force, the distributed force, as a in terms of y. Okay. So we know this is what it is at y equal to 10. This is what it is at y equal to 15. So we can just do a linear distribution here. So let's do that. So obviously, a linear distribution is going to give us f is equal to my plus b. So we knew that at y equal to 10, this was this value here, 49,050. So let's plug that in. And then the other one is 73,575. So now this is just two equations with two unknowns. We could do this. Let's do this as a matrix then. So let's say 10m plus 1b, 15m plus 1b. So this is m and b, and then the solution matrix is over here. Okay, and so you can just plug this into MATLAB or a calculator and figure this out. So let's check that. Okay, and so this tells us m is, let's see, 4,905, and b is just going to be 0. That makes sense because we're measuring it from this point. If we were measuring it from here, there would be some initial value, but we're measuring it from this point, so it's 0 at the top. Okay, so now that we have that, we need to figure out the distribution here. So let's call this, we're just going to write this as the distributed force is 4,905 times y. Okay, so now we want to integrate this with respect to y along this distance here. So it's from 10 to 15. Okay, so this is just going to give us 4,905 over 2 times y squared from 10 to 15. Let's plug that in a calculator. Okay, so we have 15 squared minus 10 squared times 4,905 over 2. So this is just 306,562.5. So that's in newtons. No, sorry, that's not in newtons. That's in Newton meters. Well, let's just move on. So the next one, we're just going to multiply this equation by y. So now it's y squared dy. And this will give us, let's see, 4,905 over 3 times y cubed from 10 to 15. So let's check that as well. Right, sorry, this one is newtons, this one's Newton meters. So this is 3883125 Newton meters. So now that we have that, if we divide this by that, we'll just get the distance in meters down y that the reaction force is at. So let's put that in here. So this is, we'll call it reaction force here, or resultant force, and that's going to be some distance, we'll call this YR, from the top of the wall there. So this is our reaction force, or resultant force, and that's when we divide that, this value here by our resultant force, we'll get the answer. Okay, so this will give us YR is 12.6 repeating meters from the top. And so why do we need to know where this reaction force is? Well, now we're going to do a statics evaluation at that point, or of this gate here. So let's open a new one here. So we have our reaction force here, and we're going to have some force over here. Here's where the pin was. So, I mean, obviously the pin is going to have some force that's stopping it from falling, but we don't, all we're taking into account is what happens here. So, if we say this is the pin, we want the moment about this pin to be 0 for the gate to not open. So, let's see, this is, we'll just call this F2. So, or the reaction force F2. So we know what FR is, we know what the distance here is. Let's check what that is again. So we know this was 10 meters and the reaction force was 12.6 repeating meters down. So that means it's going to be 2.6 repeating meters from the top here, and this entire thing is 5 meters long. So we just need to do a sum of the moments about the pin. Is equal to 0, which would be by a right-hand rule. FR would be coming out of the board, so that's a positive moment. And then our reaction force would be going into the board, so that's going to be a negative moment. Okay, so this gives us our F2 is 2.6 repeating over 5 times FR. So let's check back what FR was. FR is 306,562.5. So multiplying that by 2.6 repeating and then dividing by 5. So this is 163,500, and that's your final answer there. So basically the reaction here is doing a counter moment to the distributed load that was on that side. So that's what it takes to keep the gate closed. Any questions? Okay, so now we'll move on to the next problem. This was from your book. This is 6.105. So let's see. So in this problem, we're given this frame here. It has 3 L-shaped members and 2 external reaction forces. And so it wants us to figure out the reactions, or the reactions at point D and point B on this number here, DABC. So, as always, you want to do a free body diagram of the entire structure here. So let's see if I can do that here. May not be a great drawing, but I'll do my best. Okay, so we got something that looks okay, and so we have a pin at point G and a roller at point H. So the pin will have 2 reaction forces, call that GY, GX. The roller has 1 reaction force, which we'll call HY. And then we have these 2 forces over here. And then so we can simply do a moment about G to get this reaction force at H. Okay, so first H would have a positive moment about G, and that's a distance of 0.6 meters away here. So we have 0.6 times HY, and then each of these other forces are going to have a negative moment here. So minus 12 times 1 meter, so that's the 1 meter there, and then minus 6 times 0.5 meters. And this is equal to 0, so this will give us our HY is 25 kilonewtons. And so now that we know that, we can just do our sum of the forces here to get our 2 other reactions. So sum of the forces in the X is just GX and these other forces. So it's GX plus 12 plus 6 is equal to 0. So GX is negative 18 kilonewtons. And then GY is obviously just going to counter this HY here. Sum of the forces in the Y is equal to GY plus HY, 0, so GY is negative 25 kilonewtons. So now that we have all that out of the way, we have to start looking at individual numbers here, looking at reactions on those numbers. So obviously we know information about G and point H. I think it's probably easier, since there's only 1 reaction here, to just start with point H. Since this number we're trying to look at, we don't know any of the reactions, we can't start with that. We need to start with some other number that we know information about. So let's start with this number, HEV. This is number HEV. And let's check again. So we have this reaction force here due to the roller, and there's going to be 2 reactions at this point E, and then 2 more reactions at this point B. Just draw this thing out. So we've already here, that was 25 kilonewtons. We're going to have 2 reactions here, so we'll just call this EY and EX. And then same thing here, y and dx. So now we want to do, let's see, we can do a moment equation here to get us one other point. So if we take our moments about either point E or point B, it'll give us information about the other one. So let's see here. I guess we'll just take it about point E. So this force H is, let's see, 0.2 meters away, and it's going to give us a negative moment. And then the only other force here is this Bx. Both of these forces are acting through the point, so the only other force we need to take into account is this Bx, which will also be giving a negative moment. And so, let's see, it was 0.5 meters away. Okay, so this will give us our Bx is negative 10 kilonewtons. Okay, so now that we know that, we can actually just look right at the number we're trying to figure out stuff about. So this is for TABC. So at point C, there was the 12 kilonewtons. At B, there's some unknown value here, By, but then there's also, we just figured out, there was this 10 kilonewton force. Sorry, it's negative 10 actually. Okay, and then at this point D, let's check back what it looked like. So D was connected here. There's just going to be two reaction forces there. So we'll just call that dy and dx. So let's do some of the moments about point D, since that's the point we know the least about. So it's going to be a reaction, or this will give us our value for By here. Okay, so this By is going to give us a positive moment. And let's check back. B is 0.8 meters away from D. And we have this negative 10 kilonewtons here. That's going to give us a negative moment, but obviously since it's also negative, it's pretty much like it's positive. So let's say it's negative, it's 0.5 meters away, but then you're multiplying by a negative 10. That ends up giving us a positive moment. And then this 12 kilonewtons, so it's the same thing. It's going to be negative 0.5 times 12. So now that we have all that, we can just figure out what By is. this just gives us By is 1.25 kilonewtons. So now we can just do some of the forces in the X and some of the forces in the Y. So our sum of the forces in the X here is just going to give us dx is, it's dx plus our negative 10 kilonewtons here plus our 12 here. Okay, so this gives us dx is what, negative 2? And then our sum of the forces in the Y is equal to, we have this dy here, and then by, which we just said was 1.25. And that's it. So if that's 0, then our dy is negative 1.25. So we have our reactions at D. We had already calculated a reaction at B here, and then the other one we had found on the previous slide. So the next problem here is basically the same thing, except this 6 kilonewton force is removed. So that's going to change a few things here. So again, we'll try doing a free body diagram of the entire frame. Something like that. Then we just have our 12 kilonewtons here, a reaction from the roller here, and our 2 reactions at the pin here. Okay. So now if we do our moments about G again, we can get HY. Okay, so this is equal to 0, which is going to be our HY. Again, it's going to give us a positive moment, and our 12 is going to give us a negative moment. The HY times 0.6 minus 12 times 1. And this will give us HY is, let's see, negative, or it's 12 divided by 0.6, which is 20. And from that, we can get our other forces here. So some of the forces in the X is equal to GX plus 12, which is 0. So GX is negative 12. And then our GY, we do some of the forces in the Y, GY plus HY is equal to 0. So GY is going to be the opposite of HY, which means it's negative 20. So now we can continue similar to the last problem here with the free body diagram of this other member here, HEB. And at each of these points here, we're going to have 2 reactions. And then we have, what did we say, it was 20 kilonewtons here at H. So now we can, again, just do our sum of the moments about point E to get our value for Bx here. So again, the Bx is going to give us a negative moment, and our reaction here at H is also going to give us a negative moment. So we're going to have negative 20 times a distance, let's see, of 0.2 meters minus Bx times the distance of 0.5 meters. So this will give us Bx is negative 12. Okay, so now that we have that, we can just draw our free body diagram again of this member EABC that we're looking for. So we have this force here of negative 12. We have some unknown force here, By. We have a 12 kilonewton force acting here, and two reactions here at D, dy and dx. So again, just do summator moments about point D to get By here. So this By is a positive moment, and these other two forces are going to give negative moments. So let's see, so it's By times it's a distance of 0.8 away, and then minus 0.5 times this negative 12 force here, minus 0.5 times this positive 12 force here, which means these two are going to cancel each other out. These two are essentially, if you sum these two forces together, you're going to get 0. So the moment that they're creating is essentially 0. So this goes to 0. So if we're saying that equal to 0, we know that this force here, By, is also equal to 0. So that has the interesting effect of making dy also equal to 0 here. So our sum of forces in the y is just dy plus by, which is equal to 0. So dy is also equal to 0. And then our sum of the forces in the x, we have this negative 12 and 12 force that are canceling each other out. So dx minus 12 plus 12 is equal to 0, just gives us dx is equal to 0. So this is interesting because most of the forces here ended up just canceling out, and we end up with 0 reaction forces for most of the frame here. Okay, let's see. There we go. So in this problem, this is a bit different here. We have this sort of parabolic member here with two forces acting on it, and there's a pin right in the middle. And so this is a lot different from the previous problems we've been looking at. So we're going to want to do a free body diagram of each of these members individually. Okay. And we know but the reactions at this point B are going to be opposite if we move to the other number. So if we say this side is, we'll call this section 1 and this is section 2. So the reactions here at B, we have this by and bx. So for section 2, they're going to be the exact opposite. So bx and by. So if you don't want to get them mixed up, maybe you can label these with a 1 here and a 2 here. So we have by1 is just the opposite of by2. Okay, so then we also have these external forces acting down here and here. Okay, sorry, I just wanted to make sure I was still recording. So then we have 112 kilonewtons, 140 kilonewtons, and then we're going to have 2 reactions at each of these pins. So let's see. Let me label all this. So this is pin A, pin B, and pin C. So we have AX, AY, and then CY, CX. So focusing on for section 1, we're going to do a moment equation here. So some of the moments about point A will give us some information about point B here. So for one thing, this reaction here, or this external force here of 112 is going to give us a negative moment, and that's 5 meters away, I guess. So negative 5 times 112. And then we have this bx1 is going to give us a negative moment, and by1 is going to give us a positive moment. So, let's see. Bx is the sum of these two values here away, so it's 3.2 meters away. Minus 3.2 times bx1, and then plus 8 meters away times by1. So this is not, we can't solve this yet, but we're going to need to relate these values for bx and by, the values for bx2 and by2. So now, if we do the same thing for section 2, now we want the sum of the moments about point C. That'll give us, let's see, so we have a positive moment due to this 140 newtons or kilonewtons, so 140 times 3 meters. Then we have our bx2 here is also giving us a positive moment. So let's see. Bx was 3.2 meters away. And then our by will also be giving us a positive moment. Okay, so plus, now it's 6 meters away times by2. Okay, so now that we have these two equations, basically two equations with two unknowns here, but we're going to want to say that bx2 and by2 are essentially the opposite of bx1 and by1. So if we put this in by, this will be like a plus bx. This will be a minus bx minus by. So let's try to turn this into a matrix equation here. So we're just going to do it in terms of bx and by, not in terms of bx1, by1, all that stuff. So bx, by. So here for this one, we have a negative 3.2 plus 8, and that's going to be equal to this value here, the opposite of that value. Probably should have written these are both equal to 0. So that's why you get that. You're just moving this to the other side. So it's 5 times 112 is 560. And then doing a similar thing here, the only difference is since bx2 is technically the opposite of bx, we're going to have to change the signs of bx and by. So here we have a negative 140 times 3 is going to move to the other side. So that's negative 420. And then we're going to have negative values for each of those coefficients. So negative 3.2 and negative 6. So now that we have that, we can just plug this into a calculator to get our final values here. So let's check this. Let me just check the answer here. So I'm getting that bx is actually just 0. And by is 70. I just want to check my answer here. For some reason the book is giving a different answer. Hope I didn't make any mistakes here. We're just going to stick with this answer that we got here. So now, let's see. So now we want to figure out the actual problem was asking for the components of the reaction at A. So now that we know all of our sources here, we can just do some of the forces equation here to get that. Not sure that I really need to go over that. You're just adding the forces. And then the other part of the problem was actually just solving for these two. So we already did that. So that's pretty much the end of the problem. Then there's another problem similar to this. In this case, let's see. What did they change? Oh, okay, so they switched the two forces here. So in this case, this was the 112 and this is the 140. Okay, so again, we can do this pretty much the same way we just did the last problem. Hopefully this time we'll see if there were any mistakes made in the calculation since the book gave a different answer. So again, we can just do a free body diagram of each of these members and let's see, so we're going to say, again, this reactions here are going to be AY, AX. We have 140. I think it's probably better just to leave everything in terms of the reactions here, B, X, and BY. I think that might have been where I made a mistake. I think we just got BY and BX here, and I probably just had some sort of sign error about that. So let's try it again in this problem, see if we can get it right. So we have our CY and CX. So we want, for this first section here, some of the moments about point A is going to give us some information here. So this time, again, we have a negative moment due to everything here except for this BY. This BY is giving a positive moment. So BY times 8 meters minus BX times 3.2 meters minus 140 times 5 meters. Obviously, we can't solve for that yet, but we can use it. Some of the moments about C. Now we have this, let's see, so BX is positive, this 112 is positive, and BY is positive. So, so we have BY times, let's see, is 6 meters plus BX times 3.2 plus 112 times 3 meters. So rather than doing it with trying to do a matrix thing here, we're just going to add both of these together. And so that will cancel out the X term here. So let's see. I'm going to have 14 BY. And then whatever this is, let me just check it with the calculator. Okay, so this gives us negative 28.2 So this will give us our dy value here. I'll just put it in terms of a fraction because we get kind of a weird decimal here. 141 over 70 kilonewtons. And so we can then plug that back into our either one of these equations to get our Bx value. So let's just plug it in here. So it's 140.5, this term, minus this term, and then the opposite of that over 3.2. For some reason, it's giving weird fractions. Hopefully, I didn't make any mistakes again. But I think it's just because when we add these two together, it's giving us a 14. That's giving us, when we divide by that, it's not working out to very nice numbers. So that's what I got for that. Okay, and so now that we have both of those reaction forces, or both of the internal forces there, to get the reactions here at A, you're just doing another sum of the forces. So let's move on to another problem here. Okay, so this one doesn't look too bad. So this is problem 6.121. You have two L-shaped beams here, and then they're connected by strings. Just move them further apart. So we have just strings going straight across them, and then they're bound here by pins. And then we also have a force P acting here, and then we know these distances, so this is 2A, this is A, and this is 2A. So we're not given any specific dimensions here, we're just told in terms of A and P, and we have to, let's see, so they want us to determine the reactions at the supports and indicate whether the frame is rigid. So now let's just draw each of these individually. So we have our AY, AX. We'll call this string 1, this is string 2. So this will give us sorry, these aren't strings, these are links. So the difference there is that they can be either in compression or tension, but usually it's best just to assume that everything's in tension, and then if you get a negative value, you'll know it's in compression. So this is force 1, force 2, and then the other one is just going to be the exact opposite. So for each of these, or for either of these, you can do some of the forces in the y, and the only force on this member is AY, the only force on that member is BY. So this will give us AY is equal to 0 and BY is equal to 0. So that's a start for figuring out how to do this problem. Then you can also do, let's see, a moment equation here. So either about point A or about point B. So this moment equation, you can do it either about point A or point B. We'll just tell you the only thing that's causing a moment here, since F1 is acting through point A and point B, that F2 is the only thing causing a moment. So we can just write that as F2 times the distance of A is equal to 0, which just tells us F2 is also 0. So we've already canceled out several of the forces here. So oh, sorry, I see what I did wrong. Okay, so there was a reaction, or there was an external force here at P. So if you're doing the sum of the moments about point B, or the sum of the forces on this member, you're going to get BY is 0. But in this case, we're going to get AY is P. So let's just do our sum of the moments about point A. So in this case, since we have this force P here that's acting 2A away from point A, that's going to give us a negative moment. So we have negative 2A times P, and then a positive moment here at due to F2. So plus, what is it, A times F2. So this just tells us, but since we figured out that F2 was 0 before, due to this sum of the moments, this term just goes to 0. So this will give us, our moment is 2A times P, which means that if P is 0, it will be rigid, but if it's not 0, then the frame is going to move. It's basically like it's only partially constrained. So it's not, the reactions here are not counteracting this moment due to P. So basically you would say if P is equal to 0, then it's sort of, it's going to be static. And if P not equal to 0, then it's not rigid. Okay, and it looks like we're just about out of time here. There are a few other problems like this in the book here with different loads given or different supports here. Those might be useful to go over. I know the test is tomorrow, so hopefully this helped you guys out a little bit. And if you have any other questions, you should probably talk to or email Professor Castle or the TA. So good luck on your test. Sure.
Thank you.
And have a nice Thanksgiving. I won't be at the test tomorrow. So.
Yes.
Okay.
I'm sure he's having this test right before Thanksgiving, though.
Yeah.
Yeah, I'm like, ah.